Our goal in this video is to do two things. First, we're just going to count the number of m cycles in the symmetric group Sn. And then we're going to talk about what the centralizer of an m cycle in Sn is. So let's do this counting part first. How many m cycles are there in Sn? So remember, what is an m cycle? It's a permutation where there's one cycle of length bigger than 1. That cycle has length m, and everything else is a fixed point. So if we have one cycle of size m, the other n minus m things are just fixed points. So we can pick the m elements from 1 up through n that are going to go into the cycle. How many ways are there to do that? Well, we're just choosing m elements from an n element set. The number of ways to do that is the binomial coefficient n choose m, which remember is n factorial divided by m factorial times n minus m factorial. Okay, so we've picked the things that are going into our cycle. How many different m cycles are there moving those m elements? Well, one thing to note is that you don't get a different m cycle for every single different way of writing down those m elements. Because if you take a cycle and you cyclically permute the elements of that cycle, it doesn't change the cycle. So what does that mean? Like the cycle 1, 2, 3 is the same as the cycle 2, 3, 1, which is the same as the cycle 3, 1, 2. What are we doing? We're cyclically permuting around the three elements of this cycle. Why are these the same? Because this is saying 1 goes to 2, 2 goes to 3, and then 3 goes back to 1. But this one is saying 2 goes to 3, 3 goes to 1, and 1 goes back to 2. But that's the same three instructions, just written in a different order. Okay, so given that there are multiple ways to write a given cycle, like there's m ways to write an m cycle, by convention, what we usually do is you write the smallest element in the cycle first, and then you write the other elements. So out of these three options, go with the first one when you can. So yeah, so by convention, we'll write a cycle with its smallest element first. Example, pick 1, 2, 3 out of these three options. Okay, so we've chosen the m elements out of 1 up through n that go into our cycle. We're going to write the smallest of those m elements first. And then, how do you write the m minus 1 other elements? Every one of those things is going to give you a different m cycle. Because that cyclically permuting around, as you cyclically permute, you're only going to have the smallest thing first one time out of those m options. So you put the smallest thing first, and then you write the other m minus 1 elements in some order, and every one of those will give you a different m cycle. How many ways are there to write m minus 1 things in order? M minus 1 factorial. So what is this saying about the count for m cycles? N choose m. That's how to pick m things that are going in the cycle. And then given your m things, there's m minus 1 factorial different cycles moving those m things. Another way to do the same count is to say, okay, there's n choose m ways to pick your m things. There's m factorial ways to order those things. But then m of those orderings are just going to give you the same permutation. So you've now counted every permutation m times. So if you divide by m to deal with these cyclic permutations, then you have the complete count. And okay, m factorial over m is m minus 1 factorial. So everything checks out and it makes sense. So just to make this concrete, let's look at an example. How many 3 cycles are there in S4? There's 4 choose 3. That's 4 ways to pick the 3 things going in your cycle. And then there's 2 factorial, or 2 permutations, 3 cycles on a given set of 3 elements. So what is this saying? There's 8 3 cycles in S4. And we know that every 3 cycle is an even permutation, is a product of 2 transpositions. So these 8 3 cycles in S4 are all in A4. And when we talked about A4 earlier, a few lectures ago, we saw that there were exactly 8 3-cycles in A4. So I'm going to pause, and then we'll talk about the centralizer of an M cycle. Before we talk about what the centralizer of an M cycle in Sn is, let's remember why we might be interested in such a thing. So Sn acts on itself by conjugation. And with an action of a group on itself, what is the stabilizer of an element? It is the centralizer of that element. So if we want to know the stabilizer of the element sigma, that is understanding the centralizer of the element sigma in Sn. So we're going to pick one representative M cycle sigma. Let's take the one that says 1 to 2, 2 to 3, up to m minus 1 to m, and then m back around to 1. So what do we know? We know all the M cycles. Those are exactly the permutations that have cycle type 1, 1, 1, 1, 1, 1, 1, n minus m times. There are n minus m fixed points. And then m. There's one cycle of length m. All these permutations are conjugate to each other. They are all in the same conjugacy class. And that is the whole class. And we know that the stabilizer of any one of these elements has the same size, that conjugate elements have conjugate stabilizers. So the size of this stabilizer is always the same, even though the stabilizer itself may be changing. Okay, so how many M cycles are there in Sn? Well, by the orbit stabilizer theorem, this is the size of an orbit under this conjugacy action. It's the size of Sn divided by the order of the stabilizer of any representative element in this orbit. So it's the size of Sn divided by the order of the centralizer of this particular M cycle. But we just computed that this is n choose m times m factorial. Oh, it's not so clear. M factorial divided by m. Okay, so now there's a factor of n factorial in the numerator, a factor of n factorial in this binomial coefficient. If you cancel out what you can cancel out, what this tells you is that the size of the centralizer of an element sigma, 1 up through m, an M cycle, is m times n minus m factorial. So any M cycle, the centralizers all have the same size, and that order is m times n minus m factorial. So now we know the order of the centralizer of an M cycle, but what is it? Like, what are some things that commute with the permutation 1 goes to 2, goes to 3, goes to m minus 1, goes to m, and then m goes back around to 1? Well, one thing that's going to commute with this is products of disjoint cycles commute. So if you have a permutation that doesn't move around 1 up through m at all, that's definitely going to commute with sigma. So we have these n minus m other elements. So if you fix 1 up through m and you permute the other n minus m things in any way at all, that'll commute with sigma. Another thing that'll commute with sigma is any power of sigma. So we have the cyclic subgroup generated by sigma. That's in the centralizer of sigma. And then any product of these things is going to commute. The centralizer is a subgroup. So if these are obviously in there and these are obviously in there, then any product of them is going to be in there too. And now what is the size of the set of things we have found so far? There's n minus m factorial permutations of the other n minus m elements of 1 up through n. And then there's m things in this cyclic subgroup generated by sigma. So this set of all these products, since things in this cyclic subgroup only move the elements 1 up through m, and things in here only move the other n minus m elements, any product of these things is going to be distinct. So the total size of this set of products is the product n minus m factorial times m. We found that many elements that are in the centralizer, but that is the size of the centralizer. So if we found a set of this size that's in the centralizer, there can't be anything else that's in the centralizer. So one way to say this is that the centralizer of any m cycle, let's forget about this particular choice of 1 up through m now, is any power of sigma, and they're distinct from I equals 0 up to I equals m minus 1, times any tau in, now this notation, Sn minus m is a little informal. What this means is tau is a permutation that fixes the elements in the one m cycle, sigma, and it permutes the other n minus m elements in just like any way that you want.